Okay, this is your second video from Chapter 15, and this will be the end of Chapter 15 and the few parts of Chapter 16 that you'll be responsible for. So if you remember what your chapter outline looks like from the first video and from in-class lectures, we are just going to cover 15.7 and 15.8 here, and then some stuff from Chapter 16. So, polyprotic acids is a pretty straightforward concept. A monoprotic acid is an acid that has one ionizable hydrogen atom per molecule. So, obviously, HCl is a monoprotic acid. A polyprotic acid, well, an acid that has two or more ionizable hydrogen atoms per molecule. That could be multiple examples of that. You could have a diprotic, which would be two hydrogen ions, and that would be like H2SO4, because remember what H2SO4 can do. And then this can ionize again. Of course, the charge on it becomes more and more negative with each hydrogen ion, because each hydrogen ion leaves behind an electron. So when you lose that second one, you have a minus 2 charge. That's a diprotic. And a triprotic acid, example, would be H3PO4. And that's triprotic. It's important to realize that the Ka for each of these is different, and it becomes less and less favorable. So for something like sulfuric acid, the first Ka is going to be very, very large. It's a very strong acid, right? The next Ka will not be as large. Okay, and I forget what they are exactly, but something like the first K is going to be like 10 to the third or greater. That second Ka might be like 10 to the minus 1. And for triprotic acids, like phosphoric acid here, each Ka gets less and less favorable, if you will, for products to form, so weaker and weaker acid in each step of the way. Now, this is a pretty important concept in Gen Chem, and it's one that we often find that students struggle with. So this is acidic and basic salts. So what we're going to do here is we're going to take a look at a weak acid. So remember, HF is the one halogen that is a weak acid. So we've drawn the equilibrium arrow here instead of just an arrow straight to the right like we would do with something like hydrochloric acid, showing you that this reaction is important in both directions, if you will. And this is your standard acid-base reaction, forming the hydronium ion and your conjugate base. Now, imagine we take a salt with the same anion that's in this weak acid, so sodium fluoride as an example. This will dissolve in water to form sodium ions and fluoride ions. Now, you should realize that since this here is in fact a weak acid, right? Relatively speaking, this over here actually becomes a slightly strong base. We won't say a strong base because this would have to be a really, really weak acid for this to be what we consider a strong base. But it's a relatively strong base, which means it will react with water. I mean, it would react with a high hydronium ion and move in this direction. Now, what you have to realize, since it is a weak base, it has the potential then, if we write this in solution here, F negative aqueous has the potential simply to react with the water, right, to form HF plus OH minus, because that is effectively what we define a base as, the ability to produce these hydroxide ions. Okay, so you're adding a salt now, so there's not the hydronium ion for the fluorine to react with like there is up here, but it can react with the water. This is what makes it now a weak base. You now have this acting as a base, and this being your conjugate acid. So effectively now we're saying fluoride is acting as a base. Now, this table here shows you, if you will, if we were to had an anion of a weak acid, which is what we just had right here. That was the example we just did right here. It tells you that the aqueous solutions are going to be basic. That's what we saw here. So if I dissolve this salt into neutral water, that is at pH of 7, once it equilibrates, we will have a basic solution because of this reaction here. Right? And that's what you're seeing here in this table. That's the one we just did right here. Okay? In this case, the cation was from a strong base, if you will, sodium, because that becomes important. Because keep in mind that this potentially also has the ability to react with water. But so the way sodium would react with water would be to do this. Right? But that's not going to happen because this right here is a very strong base, so it will not form. We know that a very strong base completely ionizes in solution, so why would the reverse reaction happen? Hence, I drew the arrow in one direction. So, in order for this solution to be basic, if you will, as we see here, the anion, the F negative, this is what we did here, and this came from Na positive, has to be the case. If it were a weak base, that cation, then effectively it really will depend on the K, the individual Kas. And that's what this is showing you down here of the acids and bases. Now, let's take the reverse scenario. A strong acid, or not the reverse scenarios here, an anion from a strong acid, so let's say right here, Cl negative, right, coming from HCl, and the cation from a weak base, NH4 positive. In this case, the solution is going to be acidic because we know the chloride's not going to do anything now. It's the ammonia that's going to do something in solution, right? And that we know already because that effectively is going to react with water backwards, not going to react with water, we're going to react with hydroxides in the water to form NH3 positive no, I got this wrong. I had it right. H2O to give you H3O positive, sorry. The ammonia cation is going to react with water to give you the H3O positive plus NH3. So, in that scenario, you can see this is going to be acidic. Now, if you have a strong acid and a strong base, so like NaCl, nothing happens because you got this in solution. Neither of these reactions are going to react with water because they're derived from strong acids and strong bases, so the reverse reactions don't happen. So this is something you definitely need to read and spend some time in. It's a difficult concept. This is just showing you here the relationship between Ka and Kb. And if you actually look at, summing up these reactions, the HA cancels out. So you got the acid reaction here and the base reaction happening here. And the A negative can cancel out over here. And what you wind up with is H2O plus H2O, gives you H3O positive plus OH minus. And of course, since these are both pure liquids, they don't come into equilibrium expression. So this ultimately is just right here is what? It's just your Kw. Products over reactants. H3O positive times OH minus. We define KOW as this, remember? Okay, so effectively remember what you learned with if two expressions summed up can equal another expression, then their equilibrium constant is simply equal to the product of the other two. So this becomes Ka times Kb. That's what Kw is. And that's just a simple way of showing you that relationship because it's, they're opposite reactions, so it kind of makes sense. They completely neutralize each other. All right, that brings us to chapter 16, actually. And a couple topics we're going to cover here. One is the common ion effect. And this simply says a shift in position of an equilibrium caused by the addition of ion taking part in the reaction. So here's a particular reaction right here. And this is carbonic acid. That's the acid responsible for making natural rainwater actually acidic, and we'll talk about that in class. It goes to H positive plus HCO3 minus. Now, let's say I'm going to add to this solution sodium bicarbonate, which is baking soda. What do you think is going to happen? Well, this is really no different than Le Chatelier's principle. It is the common ion effect, and it's explained by Le Chatelier's principle. So I try to teach this as just saying this is just another example of Le Chatelier's principle. The sodium ion is irrelevant. It's not involved in the reaction, as you can see. Nowhere is there sodium, so it doesn't matter. So effectively, we're adding HCO3 minus, and what did we learn? When you add product, it's going to shift to the left. So effectively, by having this common ion of bicarbonate ion in solution, then effectively we decrease the ionization of the carbonic acid. Another major topic another of the topics we're covering from Chapter 16 is buffers. And a buffer is a solution that resists changes in pH when acids or bases are added to it. It typically contains a weak acid or base and its conjugate partner. So if you're always making up a buffer, I would want a solution in where I'd put this acid in there into solution, and then I would also add some of this. And of course, you can't add just an anion. You have to add a salt. There's no such thing as just a anion. I can't go to the shelf in my chemistry lab and get a negative. I can get sodium, A if you want, the salt of it, okay, and that would allow me to add this to solution. That would be a good buffer. So effectively, the reason you're doing this is this. You want two reactions. You want to be able to neutralize base, and you want to be able to neutralize acid. So this component right here can react with base to give you H2O plus A negative. So effectively, we have come up with a way to neutralize any added base. Well, the reason we have the A negative in there, we're going to add it by adding sodium A, if you will. Remember, HA is just a generic. The A negative now can react with any added acid to give me HA plus H2O. So we have the ability to neutralize both acid and base. That is an ideal buffer. So from a physiological standpoint, the pH of blood is buffered around 7.4, and this has to be maintained in a very narrow range, and this is the way the buffer works. Carbon dioxide as an acid reacts with water to form carbonic acid. Carbonic acid can dissociate to form HCO3 minus and H positive. You see now you have the ability effectively to neutralize any base by forming water. Okay, so I can neutralize a base with this hydrogen ion, but I can also neutralize acid, right, by this picking up this and moving in this direction, because this is a weak acid, so this arrow is double-headed here. It can move in either direction. So, and the idea is that from a physiological standpoint, if your body has too much CO2, then the reaction shifts to the right, and you get a condition called acidosis. The idea is you need to be able to neutralize that carbonic acid, these hydrogen ions that are being produced. And now, if there's too little CO2, and this actually happens during hyperventilation, then you get something else called alkalosis. That's a K there. That's too basic, basically. So blood is buffered at a very narrow pH, and it's very important. Now, the range in which it can buffer is important. And that's what makes a buffer, particularly useful. It's going to buffer within a certain range. where it provides pH protection, if you will. And it's basically going to be plus or minus 1 for the pKa. And not sure we've defined pKa, but remember P is always just means the negative log. So this is just the negative log of the Ka of your acid. That's all pKa is. So since this is a log scale, that winds up ultimately being the ratio of the concentration of the base over the concentration of the acid. And this will become clear. This is the Henderson-Hasselbalch. The ratio of those two is going to be less than 10, but greater than 0.1. That's the log factor there. Plus or minus 2 pKa units basically in each unit is a factor of 10. So now we got this range of a factor of 100 in which the concentration of the base to the acid. So you want those two to be somewhat, ideally those two would be equal. So the buffer capacity then is actually how much it can neutralize. And that's where I should say, really, this is where you want them equal amounts. So effectively you can neutralize. Now it depends. You might have a situation where neutralizing acid is more important than neutralizing base, and you might not have equal amounts if you're actually doing this from an industrial perspective. So here's an important equation. It's called the Henderson-Hasselbalch equation. It relates the acid and base components together in one equation. So this is weak acid equilibrium. This is our standard weak acid equilibrium with HA going to H3O, so H3O positive and A negative. We can write a Ka for that. Products over reactants, as always. The water is not included. This is all should be redundant to you. Now what I'm going to do is take the log form of this and just take the log of this throughout the equation. And effectively, if I do that and rearrange, what I'm going to wind up with, and you can do the math on your own, but you don't have to know how to do this, but you should actually. It winds up being the pH is equal to the pKa. I'm going to take the, I'm going to take the negative log of all these. pKa, pH equals pKa plus the log of A negative over HA and of course the negative log of the Ka is the pKa. And another way, that's where the pK is coming from, the negative log of this. And of course, you can write this in general as just saying the base over the acid, if you will. That's what the A negative and HA is. That's a very useful equation, and we'll do an example of that in class. One of the other topics, this is something that was introduced back in chapter 8, acid-base titrations, and you just need to get familiar with some of this terminology. You can look at this back in chapter 8. Indicators. This is just showing you some different color changes you actually see. It's important to realize that the endpoint and the equivalence point are not the same. The endpoint is as close as possible to the equivalence point. The equivalence point is the stoichiometric point that the acid and base are equalized. So here you see a titration of a strong acid with a strong base, and you notice this region here is very abruptly changing, and this is the case what you see with a strong acid and a strong base. They change very quickly. So in order to detect that equivalence point, I mean, ideally a pH meter could be used, but you can use the indicator that changes color, and that color change is going to take place very close to the point at which the equivalence point is reached. The last topic then is solubility equilibria that we're going to cover. And this is showing you simply an expression of magnesium hydroxide solid. And it's just convention. The solid always written on the left. We write it as a situation in which the salt is dissolving. Okay, so we can write an equilibrium expression for this, and it's going to be products over reactants, right? So it's going to be Mg2 plus times OH negative squared, and that's going to equal our K. There's no reactants because it's a solid that does not factor into the equation. And we're going to give this a special designation called KSP for solubility product. And basically, this is a measure of the solubility of a compound. What is the equilibrium concentration of magnesium hydroxide in solution when you add magnesium hydroxide solid? That is your solubility. You can report this as a molar solubility, or you can report it in grams per liter, but this is defined really. This is your solubility, whatever these concentrations are. So let's look at this. And the expression here, this particular KSP here is equal to 5.6 times 10 to the minus 12. We now know that is equal to the concentration of magnesium 2 plus ions times the concentration of hydroxide ions. And what we're going to do is we're actually going to solve this in class. So you take a look at this. You can use a Rice table here and put in some X values for these and solve it and see what you get. And effectively, what I will tell you is that X is equal to the solubility, because X is equivalent to the dissolution. This is X of that salt. Okay, you're going to wind up with twice the amount of hydroxide in solution that you do magnesium, but the solubility of the salt is a 1-to-1 relationship between here and the magnesium. And when you set up your Rice table, this will be designated X and this will be designated 2X. So your X is the solubility of your salt. Lastly, you have factors affecting solubility, and effectively this really is just Le Chatelier's principle again. Here we have a KSP for this particular reaction, which would just be barium ions, right, times sulfate ions, right? And the idea here now, this ion here, if I was to add to this solution some sodium sulfate, then the presence of that sulfate ion here will decrease the solubility of barium sulfate, right? So that's what we're saying. The solubility of this will be less in a solution that contains sodium sulfate than it would be in a solution that just contains pure water. Okay, so one last effect here. You see the same thing here. Here's the solubility of calcium fluoride. And what we're saying here is that by adding an acid, like it doesn't matter what the acid is, we'll just designate it as H+, that can react now with the F negative to form HF, because F negative is, remember, is a weak base. So as F negative is consumed, the solubility of this salt increases. So effectively, the solubility increases as the pH decreases. Let me just write that, and that will be the end of our video. That's one out there. Solubility increases, I'll use an upward arrow, as the pH decreases. I'm sorry. That's right. And with that, I think that is the end of our video.